I'm very happy to be here instead. And thanks. So this work is based on a number of articles in collaboration with these guys. I hope you can read. And yeah, so I'm going to talk about precision tests at the Large Hadron Collider, or also more generic. In particular, trying to understand what we can understand from this test. So I think it's impressive how in the last century we have refined our exploration of the universe at different distance scales. And now basically we control our understanding over more than 40 orders of magnitudes. And on the largest distances, this exploration is basically limited by the size of the very visible universe. While on the smallest instances, the frontier is set by the Large Hadron Collider. And this very fact, so that the Large Hadron Collider defines the energy frontier, shaped also how searches at the Large Hadron Collider were done so far. In fact, in the first phase of the LHC, it's starting up in 2009 until 9, the typical way in which we searched for things beyond the standard model was by searching for well-visible features that would stick up on top of the standard model prediction. And this was motivated basically because the Large Hadron Collider defined the energy frontier, so it was providing the first exploration in this region. And so these type of features, well visible, will be the first one that you would see. But also, they will be the easiest one to start, because imagine that you find something like this sticking out from the background. The fact that you can measure the background on both the left and the right side means that you can somehow measure this feature very well. So it was the first one to be seen, the easier one to study, and also these type of features were predicted in many models, typically weakly coupled models beyond the standard model. So basically, this type of exploration was the most well-motivated thing to do. Now, things are going to look very different in the future of the Large Hadron Collider, because basically the journey up in the energy is finished, and it will evolve along the intensity frontier, meaning that more and more data will be accumulated until 2035. Basically, the Large Hadron Collider is supposed to switch off. So this type of new exploration gives us access to a new type of information that goes under the name of standard model precision tests, and basically aims at measuring precisely tiny departures from the standard model prediction. So not well visible things, but tiny features. And these are interesting because they're believed to be associated with the existence of new scales, new particles, new structures at much higher distance scales. So in some sense, the standard model precision tests really give us access to the next level in energy. They will define the new energy frontier set by the LHC. So the language to relate these standard model precision tests to these new physics is that of effective field theories, in which basically the effect of a new massive state, that energy is much larger than the one that we can see directly at the LHC, is characterized by an energy expansion, so new effects that decrease with as you go down in energy, the energy over the scale of new physics. And this type of exploration is much more challenging than the one we were doing so far, because remember, you could understand you could understand the background just from seeing it on both sides. Well, here you really have to calculate it within the standard model, and you also have to measure all these points very well in order to find a departure from it. And what I like is also that from a BSM theoretical point of view, this type of features is typical of strongly coupled models, because basically a weakly coupled model sitting at the same mass scale would have a much smaller impact at low energies. So you see that the future of the LHC and the past are very different. In the past we were looking for well-defined features associated with weak coupling, and in the future we will be looking for very hard to disentangle features possibly associated with a strong coupling. And there are two ways in which we can somehow hope to find these effects. But they can be both understood by looking at the simple formula, which basically is the cross-section for these new effects, where I've factorized out the standard model. So the first one is basically to look into places where the standard model is very large, so that you could see tiny deviations from here just because you have some process which is performed many times. And this corresponds to basically sitting on standard model resonances and trying to find, for instance, deviations from the coupling of a standard model particle on the resonance. This is what they were doing, for instance, at LEP, right? They were producing Z bosons millions of times, trying to test their couplings very well. The other possibility is instead to go in a region where the signal is enhanced, not the standard model piece, because just it grows with energy. And my talk is going to focus on this region. I'm going to talk about high energies scatterings at the Large Hadron Collider. And in particular, the first high energy scatterings are 2-to-2 processes, and this is what I'm going to focus about. These are all the possible processes you can have, just classified in terms of fermions, scalars, and vectors. I'll come back to this in a second. And so basically in this talk, I'm going to focus on 2-to-2 processes that exploit the high energy reach of the Large Hadron Collider, and I'm going to discuss, at least initially, what are plausibly the leading effects that you could expect from these theories beyond the standard model. They are captured by dimension 6 effects, dimension 6 operators that represent the leading deviations from the standard model Lagrangian. Okay? So, before telling you what we can learn from these tests, I will like to present you a number of obstacles that we have to overcome in order to perform these tests. And I mean, these tests are super difficult from many points of view. As I told you, we need to understand the standard model very well, so to reduce the systematic errors when doing this sort of searches. We need to perform a lot of collisions in order to reduce these error bars and so have a lot of statistics, but there are also some fundamental issues that are between us and this precision problem. And these are what I'm going to talk to you in the first part of the talk. So, as I say, these are all the amplitudes, just schematically. Basically, a scalar here means either Higgs or the longitudinal polarization of a vector. And this can be a vector, a gluon, or whatever. So, one first feature that you can see by looking at the standard model that affects these amplitudes with an odd number of scalars is the following. The standard model Lagrangian has a Z2 symmetry that basically brings a scalar into the minus scalar that is only broken by the small Yukawas in the standard model. Okay? So this implies that basically when you're looking at processes with an odd number of scalars, typically you pay the price of a VEV, of a Higgs VEV, right? Just out of to present this Z2 symmetry. And basically, out of dimensional analysis, this implies that all amplitudes with an odd number of scalars, unless they involve the top quark Yukawa, which is big, but in the limit of small Yukawas, are going to be suppressed by this factor, which for high energy collisions at the Large Hadron Collider is of order 90% suppression. Okay? And just to give you a practical example of this, one thing that people look in physics beyond the standard model is this parameter kappa gamma. You don't need to know what it is. It's a anomalous triple gauge coupling. But what you need to know is just that this parameter modifies both the amplitude for a longitudinal W and a photon, or two longitudinal Ws. And in fact, when you look at the constraints that experiments obtain looking at both processes on the same parameters, the one with a transverse guide, so with an odd number of scalars, is in fact looser. And this is an example of this suppression. So this is the first obstacle to precision. These three amplitudes are not very sensitive to the high energy regime. Another obstacle is just an accident, the fact that there are some amplitudes which are not modified by dimension 6 operators. And these are in particular amplitudes with neutral gauge boson in the final state. So for instance, the production of a pair of Z bosons from fermions, or just ZZ or photon-photon scattering. This is a bit unfortunate because, okay, we're looking at the at some effects which are small, dimension 6 operators, but they are not there. We have to look at dimension 8, which are even smaller. And it's unfortunate in particular because these processes with Z or photons are something that we can test very well. So in principle, this could have been good probes for new physical effects, but they are not. A further obstacle in this precision program is concerns all amplitude with at least one transverse vector. And basically, it has to do with some non-interference patterns, which I'm going to now explain in detail. The idea is that at the Large Hadron Collider, basically the boost factor of these particles is very high, very large, for 10 or bigger. So that you can think of all the states as having a very well-defined helicity. And you can compute the helicity for the 4-point amplitude, both in the standard model or in physics beyond the standard model, where here I mean the amplitudes where I have just one insertion of these dimension 6 effects. And the result is given here in the massless limit, as I said here, and just looking at 3-level amplitudes. So this is pretty important. So let me open a parenthesis and tell you a bit more about it. So how do we find the helicity of a 4-point amplitude in the standard model and in DSM? It's just a set of small rules, and they're pretty easy, so let me go through it. So the idea is that when you're looking at an amplitude with n legs formed by two sub-amplitudes with smaller number of legs, where the total helicity of an amplitude is just defined with all outgoing momenta. So the idea is that the total helicity of the combined amplitude is just the sum of the sub-amplitudes, simply because they are defined with outgoing momenta, so here I have to match one opposite sides. Another rule that will help us understanding the helicity of 4-point amplitudes in the standard model is the fact that the 3-point amplitude is very well constrained, well, is uniquely fixed by just by fundamental principles based on Poincaré invariance, dimension analysis, and 3-point kinematics. And the idea is that these three requirements per se uniquely fix the form of these amplitudes in terms of the helicity of the external legs. And what you get, because dimension analysis is involved, it turns out that the modulus of the total helicity is just given by 1 minus the dimension of the coupling that goes in here. So in the standard model, in the high energy limit, which basically I defined it as the limit in which only marginal operators survive, so G is dimensionless, and the 3-point function, whatever 3-point function in the standard model, all of them have total helicity 1. Okay? A third rule that we use to understand the helicity in the standard model has to do with the supersymmetric word identities. Now you will ask, why supersymmetry? We're talking about the standard model, but I think it's very nice to notice that in the standard model, if you switch off either the up Yukawa or the down and lepton Yukawas, then the standard model can be uplifted to a supersymmetric theory, in the sense that you just take the standard model fields, promote them to supersymmetric multiplets, and because now basically you have you don't have both H and H dagger appearing in the Lagrange. You have just either H or H dagger. So for this reason, you can just promote it into a theory with a holomorphic superpotential. with one Higgs double. And this theory has also R parity, which means that basically when you compute an amplitude with external states in the standard model, because of R parity, you cannot have a mediator in between that is supersymmetric, right? Only the standard model guy will survive. This means that basically when you can take this theory, which is supersymmetric, and as long as you compute amplitudes which in the external state have only standard model particles, you can actually use supersymmetry, but without having supersymmetry. So supersymmetry is just there as a tool, but it will not enter in the amplitude. And so you can use the advantage of supersymmetry to show a number of beautiful features. For instance, the fact that amplitudes with all positive helicity vectors vanish. And let me skip the details, but basically you can show that just because the supersymmetry generator annihilates the vacuum, all these amplitudes, which in the standard model would have total helicity equal to 2 or 4, they actually vanish. So we're left with a situation in which almost all amplitudes in the standard model have total helicity 0. Just by putting together these three ingredients I told you about, you get this nice feature. As I say, basically your total helicity of this is 1, plus minus 1, this is also plus minus 1. When you sum them, they can give you 0, minus 2, or 2, but 2 and minus 2 are basically impossible because of word identities, and you're left with all amplitudes having helicity 0. That one can have helicity 2 because it's you can have an amplitude which is made by fermion with a Higgs exchange with an up and down Yukawa. So in the limit where up and down Yukawa are different from 0, this supersymmetric argument doesn't work. So that's why we're here. Okay, good. So this is just a short parenthesis to tell you how that all 4-point amplitudes in the standard model have helicity 0. Now, what about the physics beyond the standard model? Well, the first thing that I tell you is that the supersymmetric word identities do not work in physics beyond the standard model. In particular, all operators which have a transverse vector are not supersymmetrizable. In a sense, you cannot play the same trick of just extending it into a supersymmetric theory. Here, you need some SUSY breaking effects. Okay. And so let me look at all operators which you can have, which you can write at the level of dimension 6 Lagrangian, right? I don't know if you heard already the people quoting 2,499 operators at the dimension 6. Anyway, they can all be written in this form. And in fact, there is only one that contributes on shell to a 3-point amplitude, and it's basically this F mu nu cube, so just a field strength cube with the appropriate Lorentz contraction. In this case, this formula, which relates the total helicity of the 3-point amplitude to the dimension of the coupling, still holds. And but now, since we are in a theory with dimension through coupling, because the dimension 6 Lagrangian is dimension 1 over mass square, basically this formula tells me that the total helicity of the 3-point function is 3. Okay? So when I look at the helicity of the 4-point amplitude with one insertion of this 3-point vertex, I just sum the things, like helicity plus minus 1, helicity plus minus 3, and I get that the total helicity is plus minus 2 or 4. Okay? So I don't get 0, which is the one in the standard model. There are a number of operators which contribute on shell to the 4-point amplitude, and in fact these are local operators that contribute directly to this 4-point amplitude, and they're built with objects which have which source states with well-defined helicity, for instance fermions with positive or negative helicity, and the field strength as well can be decomposed into two pieces, one which always sources positive helicity and one which always sources negative helicity. So basically, out of just this considerations, you can understand what helicity is sourced by any of these operators. Finally, there are two operators that contribute only to the 5 or 6 point amplitudes, And so basically, their contribution to the four-point amplitudes will be suppressed by powers of the scalar VEV over the energy. So basically, they are going to be suppressed in 2-to-2 process, and I'm not going to consider them any further. Good. With these considerations, you can basically see that the total helicity for amplitudes, 4-point amplitudes in physics beyond the standard model, when a transverse vector is involved, it's always different from the standard model one. Okay? So what does this imply? Well, the implication is that, of course, these two don't interfere just because they are different objects. So when I look at the cross-section for the standard model plus some BSM effects, the interference term vanishes, and you're left only with the quadratic terms. So remember that we're looking for something which is supposed to be a small departure from the standard model. And now we realize that the small departure is even smaller because I have to take the square of it. So this is my third obstacle to precision. Okay, so it took me a bit long to explain, but I think it was worth the effort. Amusingly, of the amplitudes that do interfere, so the ones which have scalars, for instance, instead of transverse vectors, you would think, okay, good, this is now interfered, they have everything that I need. But the problem is that in typical scattering experiment, you're not measuring actually the polarization of states. So, for instance, when you do WW scattering, it's very hard at the LHC or in any of these colliders to actually understand whether your W is longitudinally or transversely polarized. And what happens is that when you look at the contribution to the total cross-section from longitudinal states with respect to the one of transverse states, it turns out to be incredibly suppressed. This is, as discussed in this paper, basically they look at, in a particular kinematic region, at the ratio between longitudinal and transverse, and they're looking basically at the first thing that you can measure in this, if you modify this thing by this parameter A, and they find this incredible suppression coefficient, 2000 in the cross-section. This is just an accident built up of 2s and 3s that eventually sum up to 2000. With naive dimensional analysis, you will never get this. So this is something you really don't expect. And something similar happens when you just look at the amplitude for WW per production. For instance, at LEP, we were doing E plus and minus collisions above the W threshold. They were actually testing this very process. And here is the same. This is the cross-section as a function of cos theta. This is the angle of, for instance, one of the W's with respect to the incoming E plus and minus. And even if you look in the place where it's more favorable for the longitudinal one, where it's at its peak, it's suppressed by a factor of 20. Again, something you will not guess by dimensional analysis. So, of the amplitudes that do interfere, well, they turn out to be suppressed in their contribution to the total cross-section. So they're not very good probes of BSM either. So you see that we have quite a lot of problems in this standard model precision test program, because almost all of these amplitudes, they have one or another fundamental obstruction in order to actually see deviations in physics beyond the standard model. So, accepting that there are these obstacles, let me now ask the question of still, what can we learn from these tests? And in particular, I will start with the following perspective. Okay, good. We have a lot of obstacles, so it's hard to make really precise measurements of this physics beyond the standard model. Yet, we can search for things which are naturally big. Remember at the beginning I told you that strongly coupled physics will actually have large effects as opposed to weakly coupled physics that for comparable new physics scale would be small. Okay? So let me ask the question of what what kind of new strongly interacting physics can we have in physics beyond the standard model. Now, the first objection that you might have is that, okay, well, we observe the standard model. Typically we perform, or at least we know a lot about small energies. For instance, the lab collider made a lot of tests of the standard model at small energies, and everything totally appears weakly coupled. So how can I possibly envisage a new strongly interacting sector at higher energies? And the way you can envisage this is if you have some approximate symmetries that somehow distinguish between this new sector and the standard model. So there will be a sort of shielding effects from this strongly interacting sector and the standard model. And to be more concrete, what I have in mind is a sector beyond the standard model, which is characterized by one physical mass scale, m. Physical meaning that there really are states there, so this is a state in which I produce new particles, and one coupling, G star, which I assume to be strong. Strong meaning very large, even up to 4 pi, but still I will treat it as a perturbative coupling, in the sense that I can somehow associate some perturbative physics, a bit like large N QCD. And then this new sector is also characterized by some symmetries. And the idea is the following, that basically at these high energies, this new sector produces some interaction, a theory with some interactions which are irrelevant. This is reminiscent of some non-linearly realized symmetry, for instance. So higher dimension operators, irrelevant operators, do respect the symmetry, while I also have in mind a small relevant deformation of this effect. So that basically, when you go down in energies, all these irrelevant things which were really associated with these new strong couplings, they will disappear just because they are irrelevant, and I'm going to be left only with a dimension 4 Lagrangian, which came from a perturbation up here, and I identify this with the standard model Lagrangian. So that's what I want, something that flows at small energies to the standard model, but high energies it can be very different. And in fact, you can see this directly in the amplitude for 2-to-2 scattering, which has dimension of a coupling square. So this is really testing this possibility. At small energies, I just want these amplitudes to match to the standard model couplings, while at high energies, I will gradually approach this new strong coupling. Okay? So let me be more explicit. One context where you might have encountered this is that of composite Higgs. Then the idea is that the Higgs is just a pseudo-Nambu-Goldstone boson of a new strongly interacting sector. For instance, people have studied in much detail this symmetry breaking pattern in which I have a global symmetry SO5 broken down to SO4, and this gives me exactly 4 Nambu-Goldstone bosons which are identified with the 4 degrees of freedom of the Higgs. Okay? In this setup, you do have a symmetry, which is a shift symmetry, non-linearly realization of SO5 on the Higgs. And what the symmetry does, more or less, I mean, the way you construct the interactions of these symmetries through the CCWZ Lagrange, but basically what it does is that interactions that involve derivatives somehow are allowed by the symmetry just because it's a shift symmetry, while interactions that do not involve derivatives are forbidden by the symmetry. And the result is that, in fact, irrelevant operators of this type with derivatives can really come from this new strong sector, so they can be really associated with this new coupling, G star, very large, while relevant operators without derivatives are instead naturally small, as lambda in the quartic coupling in the standard model Lagrangian is a small parameter compared to this large coupling. And the result of this type of models is that in fact when you do scattering of longitudinal vectors or in principle also scattering of Higgs particles, your amplitude for 2-to-2 scattering will be at small energies, where this piece vanishes, it will be just given by the small parameter lambda, while as you increase the energy, you will be more and more sensitive to this new coupling. Eventually, at energies of order n, you will be really testing this new strong interaction. Okay? Right, so this is something that's already well known in the context of composite X. And so for scalars, we already have a very well-defined situations in which you can have this feature, strong interaction associated with symmetry that flows at low energies to the standard model. Now, my question is whether something similar can happen also for the transverse polarizations of vectors, because remember that many of these obstructions to precision were associated with the transverse polarization of vectors because they had this non-interference pattern and so on. So can actually the transverse polarization of vectors be strongly coupled? And initially you would say, well, not so much, because usually you associate these vectors to the gauging of symmetry, so that basically eventually all the interactions involving the vectors will be associated with just one coupling. And we have measured this coupling very well at small energies, so I'm not expecting anything to be changed, or I don't expect the possibility of being able to include a different interaction at high energies. This is not quite true, because there are in fact two ways in which you can couple a vector to some matter. Either through the monopole interaction, which is exactly what you have in the covariant derivative, or through a dipole type interaction. In principle, the coupling of these two guys doesn't have to be the same. So let me envisage the following scenario, in which you have a composite vector, a mu, characterized by a strong coupling, G star, and it happens that all degrees of freedom in this theory, this phi, don't have a charge. All light degrees of freedom, they don't have a charge. They just happen to have to be composites of some constituents, which is charged under this mu, but they happen all to be neutral. Yet they can have a large dipole, just because they have components inside. So the Lagrangian at small energy will have a form more or less like this one, in which this vector will only appear through its field strength. And in particular, the other degrees of freedom will just be associated with a normal derivative. They don't have a charge, so the only way they can interact with this f mu nu is with this vector is through this f mu nu. So what happens in this setup is that you can have some interactions between this vector and the other states, or also between the vectors themselves, but they can be strong, but they are all irrelevant, and they are characterized by these multiple kind of thing. This is what happens, by the way, in the Euler-Heisenberg Lagrangian, when you integrate out the electron. Okay? Now, let me consider a small departure from this limit, in which I add one little constituent here to unbalance the neutrality of this state by just a tiny factor, which I define in this way. A tiny charge, which will allow me to define this smaller coupling G. Okay? This is small, this is big, and this is also small. Okay? So, in this limit, with this deformation, now I do have a light degrees of freedom, which is this guy, which is now charged, okay, by a small charge, and this Lagrangian will be modified by a very tiny amount, in which I just include one interaction through this monopole type. But since the charge that I've added here is just one, as opposed to the many charges that made up the dipole, this coupling can be much smaller than the one associated with f mu nu. So basically, I've deformed this picture in a picture in which now I do have a weak coupling, but it's marginal. Okay, it comes to the monopole. So basically, this allows me to have exactly this picture in which I have some strongly irrelevant interaction and some weak marginal interactions. And I like to view the non-abelian extension of this as a deformation of the symmetry, because the symmetry associated with the weak gauged interaction, for instance, if I'm looking at the weak interactions SU2, it has the geometry of a sphere, just SU2. While in this limit, where I just have f mu nu interaction with f mu nu, This is characterized by you have a U1 symmetry with an SU2 global, so it's actually a plane. So if you want, this process of going from this limit to that limit is just a flattening of the sphere. It's called an Inoue-Wigner contraction, in which I'm just zooming into the sphere. So you see that the limit of weak coupling and strong coupling are separated not by exactly a symmetry like you normally have in composite X model, but a symmetry deformation. So it's not a different symmetry, but a different limit of the same symmetry. So the implications of this setup, in which I do now have strongly interacting transverse vectors.
Sorry, can I ask a question? I think, I mean, I think I discussed this with Ricardo before. I think he agreed with me. Do you agree that you could also get this just if you have, if you just imagine that you have some heavy charged states and they just have much larger charge? Or in
you mean larger representations?
Case, or in a non-abelian case, or in big representations?
Totally. No. In fact, that's a very nice microscopic picture. Yeah, no, I totally agree.
That basically means the loops of the just very pedestrian level, the loops now of those things have this big Casimir enhancement, right?
Totally. No. In fact, that's a very... it would be the analog of this abelian case for the non-abelian.
In some sense, that's kind of what you have in your constituent picture. You can't have these constituents without having some states that have very large charge, right? So it's actually the same thing.
Yeah, no, I totally agree. It's a nice way of seeing it, more explicit. So the implications of this setup is that now you do have expect large effects in this type of amplitudes, and this is what experimentalists are already looking at the LHC, right? And so basically they're already putting constraints on this type of setup, and the constraints are on this form, and let me show them to you just on this plane. Basically, this is the mass scale of this new sector, and this is the strength of the coupling, and so it's constraints from this triple gauge coupling analysis, and this is quartic gauge couplings. They map to these two areas. This is tinier because basically it's just the operators that source this thing are more irrelevant compared to this. They are dimension 8, so the constraints are naturally weaker. But this is basically what you get. Now you might think this is not much. In fact, we're talking about these weird new interactions associated with scales below 2.5 TeV. So you would think, okay, good. If I have this, probably I would have produced resonances and whatever already. So this is not much of information. But
so can I ask yeah. Going back, can you just go back to do VBF type diagrams, vector boson fusion type diagrams also contribute to this?
Yeah, totally. They're still
schematic that you're drawing these diagrams? Or?
Exactly. Sorry, here I didn't put it. In fact, this this one, gamma gamma WW, this is a VBF type of thing. It's basically they are they're the two protons, they emit photons and they go to W's. So it's a VBF type of diagram, but with photons in the initial state. It's a bit cleaner, and at the moment is the one that provides the best information.
Okay, and then, sorry to be slow, but then in terms of the 3-point couplings there, is there any of these, were there any of these obstacles to precision that apply to the 3-point?
Totally. This one had many of them. This one had we had just the non-interference one. So basically what we're doing here is the fact that we're pumping up the coupling so much, we're no longer actually thinking about this effective filter effect as a small perturbation on top of the standard model, but they can be bigger than the standard model itself, and at some energy scale. So the fact that it doesn't interfere then doesn't play such a big effect, just because the square it's huge. So yeah, you might think this is not much of a deal, but you have to appreciate that this is the only type of structured scenario that actually motivates those searches. So when you're thinking of triple gauge coupling analysis, basically, I think this type of picture is the only one that at present really can be used to interpret these searches. Okay. Right. Now, so I try to argue that large effects. Who cares about precision if we are actually looking for large things? But still, it's interesting to ask ourselves, okay, imagine we had precision, imagine we didn't have all these problems. What could we have got out of this standard model precision test? And in fact, remember that when I showed you all these obstacles to precision, there was one diagram which didn't have any color around it, didn't have any type of suppression, which is just the scattering of 4 fermions. So let me focus on this one and use it as a sort of example of what precision can buy. So let me go back to these models that I've been discussing so far in the context of transverse vectors. And basically, since you modify the physics of transverse vectors, you're also modifying the propagator through this type of operator. If you're familiar with physics of the large electron positron collider, you might be familiar with this article, and basically these parameters were called the physics entering this 2-to-2 fermion scattering was parameterized according to these W and Y parameters. This is basically an extension of Peskin and Takeuchi S and T parameters. And so people, I mean, basically proton-proton to lepton-lepton is one place to find this type of physics. And in fact, in this nice paper from last year, these guys made an analysis trying to constrain this vertex, and well, I'll tell you already, they found a constraint on the scale of order 2.8 TeV. But the way they did the analysis is that they put a cut, so they put a constraint on the energy of the process. So they basically, by increasing the energy of the process, you're seeing what is the typical energy that you're using to constrain your new physics. And what you find is that by using data below 2 TeV, you constrain a scale of 2.8 TeV. So somehow this is consistent with effective field theory, if you were wondering whether or not testing such low scales is still a good idea using effective field theory.
Can I ask you, this thing here though, I thought that you had said that the fermion amplitude, the standard model had helicity 0 unless you had both the up and the down repowers, right?
Exactly.
Which is a tiny amplitude, so I would think you would have effectively have the non-interference in this case as well.
Well,
right?
the thing is that here you're talking about in the standard model as helicity 0 mostly, but also the BSM one has helicity 0.
Oh, I see.
Because basically you're here it turns out that those helicity rules for BSM amplitudes they give you also 0.
Okay.
Another place to look for this type of things is dye-jet analysis, and in fact, this is already presented with the new 13 TeV data, which basically goes at much higher energies, and the constraint on this type of physics is much stronger. So in fact, what I was telling you before, it's already daunted by this LHC analysis that go all the way to 3 or even 6 TeV. This is just looking at dielectron processes. So in fact, this is what precision buys you, right? I'm looking at an amplitude which is not even enhanced by the strong coupling, because basically here I don't see any strong coupling. This is just associated with the energy expansion, right? While the processes before, remember, these guys really, their contribution was big, enhanced by 4 pi. Now here I'm not enhancing anything, and still, just because of the precision, I'm actually getting better constraints than these other guys. Okay.
So why was this? You just said very quickly there was an experimental analysis. Why was it so much better than?
Well, sorry, this one. That one?
Yeah.
Well, this is just because it's 13 TeV. It's dye-jet, but it's 13 TeV.
Oh, this was a study.
This is still 8 TeV.
I see. This was just okay.
Probably after today, more young, there's going to be also the other one updated, but it's just okay. So good. then just before concluding, let me ask the question: what else can we learn from this type of diagram? Right? So it's so good; it evades all my possible obstacles. So let's see all the types of physics that we can from which we can learn something by studying this. I told you that we can learn something about the physics of transverse vectors, just because they propagate in between two fermion currents. But in fact, this diagram teaches me even more about fermions. And in particular, if fermions are composite or partially composite, so that they are somehow in this type of scenario you encounter them in many composite X models where also the fermions are partially composite, random syndrome, all these things. And then the type of effects that you expect here have this form. It's just a fermion current square, and they really are enhanced by the new coupling because you're probing the new strong interactions. And in fact, even as example, just looking at budget per production, assuming that these are maximally strongly coupled, and just taking for an example the downright to be fully composite, I get that the scale of new physics is 40 TeV. So we do know a lot about this type of scenario. I mean, we know that they are certainly not there up to 40 TeV. So this is as far as this frontier from the Large Hadron Collider can push the possibility of new physics. Okay? And since I still have some more time, let me bring this a bit further. There's another type of hypothesis that we can make and test in these four fermion processes. Now, you all know that supersymmetry, when it breaks spontaneously, it gives you a massless Golstino at low energies. And in fact, this Golstino, similarly to the Goldstone boson coming from the breaking of a spontaneous internal symmetry, has some sort of shift symmetry, but it's much more complex just because it has to do with space-time symmetry, supersymmetry, and has this form. So the Lagrangian for Golstino has this form in which I have a kinetic term, and the first interactions are these ones, and they arise at dimension 8. So the Golstino doesn't have any dimension 6 interaction, just because of this symmetry. Now my question is whether perhaps the standard model fermions themselves can be approximate Golstini. What would be the implications of that? So the first one would be basically that similarly to what I was showing you before, the dimension 4 interactions would now not respect supersymmetry, so they would be protected and small. This would be a scenario in which I really have my new interactions, perhaps associated with a strong coupling, separated from the ones of the standard model, the marginal ones, and I will not have any dimension 6 interactions. They would also be suppressed just because they do not respect supersymmetry. So this would be a scenario in which the fermions would have the standard model interactions at low energies, and then slowly, or fastly, I don't know how you want to see it, this new physics effect pop in with an energy dependence which is just proportional to the energy to the 4. And you can test this possibility, again using this 4 fermion scattering, and you find that basically the limits are for the just 10 TeV for the derived pseudo-golstini, so in similar footing as the one I was telling you before of partial compositeness. There the bound was 40 TeV, here is just 9. Or if you want all the standard model fermions to be pseudo-golstini, the bound would be about 20 TeV. Now, why do I think this is interesting? Well, I think it's interesting for a number of reasons. The first one is that we are always used, or at least the benchmark for physics beyond the standard model is effects that grow with E squared over M squared, right? Well, this is a structured scenario with somehow softer interactions that grow like E to the 4. Now, you would ask me, okay, good. Are even softer behaviors possible? And the answer, it depends, right? You can make very generic assumptions, so just asking that the UV theory is unitary, and then the answer is no, I cannot have e to the 6 behavior, just because you can have some positivity constraints, as pointed out in this paper, that imply that if you want your UV theory to be unitary, then you cannot have a symmetry that kills all interaction up to this and consider this symmetry exact. So contrary to supersymmetry, which basically killed everything up to e to the 4, you cannot have a symmetry exact that kills everything up to e to the 6. So somehow generic assumptions, a generic class of theories only have behaviors up to this guy. Yeah, I think it would be very interesting to study theories with enhanced soft behavior, like the one that Jaroslav and collaborators studied for scalar, to study in general their effect in these standard model precision tests as some other perspective on how physics beyond the standard model can modify processes of the Large Hadron Collider. So, the message I wanted to give you in this talk is the following. This standard model precision test lie beyond the LHC direct reach, and it strikes me to think that perhaps in a few decades the legacy of the Large Hadron Collider will be actually this standard model precision test. They will define the new distance frontier reached by the LHC. And in particular, the fact that Large Hadron Collider has interactions that probe very high energies implies that the LHC is very good in using these 2-to-2 processes. However, this came with a lot of challenges, besides the ones that people traditionally think, associated with experimental systematics, statistics, and the calculations in the standard model, which are getting more and more complicated. There are some fundamental obstructions, such as this non-interference, or the fact that some of these effects basically are suppressed in the total cross-sections. Given these obstacles, the most that we will learn about this frontier will be in the context of strongly interacting theories. So, for instance, composites, fermions, or these multipolar vector interactions that I mentioned in the talk. And then the kind of process that can give us most of this information, that really pushes things forward, is this 4-fermion interaction that doesn't suffer from any of these situations. In this 4-fermion interaction, we can learn about different type of BSM scenarios. Each of them comes with a different power counting, basically a different way in which it will reflect its properties in the low energy theory. Standard model, this amplitude just goes like a coupling square, while if the new physics is in vectors, the amplitude goes like a standard model coupling square times this this ratio of energy over the scale of new physics, and the constraints were for 6 dB. If the new physics actually affects the whole amplitude, not just the W propagator in there, then it can become much stronger. It can really probe the new strong interactions, and the constraints in this case for strongly interacting physics is huge, 40 TeV. While if we are probing the strong interactions, but there is some symmetry selection rules that implies that the interactions are softer, then the constraints are much wider. So this scenario can also be somewhere close to us. And I hope to have convinced you that this BSM perspective, in which I have well-defined hypotheses and I look on how to test them at Collider, is important, not just to define what we want to search in the standard model with precision test, but also to actually understand how good the standard model is. Because if I just say, good, I measured something at the percent level, and that's supposed to tell me how good the standard model is, I don't have any quantitative meaning if I don't compare the standard model with some concrete hypothesis in order to understand which one performs better. Okay, that's enough. Thank you very much.
No question? So did I understand correctly that then if the new physics is in the vectors, you are literally probing these x and y parameters, and so the statement is that the LHC is now blown LEP out of the water for those precision tests. Is that really?
Well, right now it's a bit better, but it's not yet blown out.
It's a bit better,
yet.
but it's not. Okay.
But with the 13, with the future, from now on, it will basically make better and better, just because it's high in energy. So the crucial thing is that already now we're probing these interactions with leptons. In the standard model, we're probing them at the 10% level at high energies, so for the 1 TeV. So it's 10% at 1 TeV. This thing grows like energy square, so you get another factor of 100 just from the energy increase. And so it's a bit, and basically that's how you get to the per mil level, which is what you got at the and then was the contrary. You have percent level precision with a factor of 10 energy increase, and here you go.
Any questions? All right. Well, Francesco will be here today and tomorrow. So, and if you want to, interested in going to dinner tonight, you can talk to me. Let's thank him again.